So let's get started. Welcome to this revision session of Introduction to Semiconductor Devices NOC 23E82. This is 13th week on October 21, 2023. My name is Amit and I am a PhD student at ISA Bangalore. So this is going to be summary, but just a summary of the previous session. So first we talked about the material classification. Basically, we talked about the conductivity, that use based on conductivity you can classify the materials as insulator, semiconductor. Then we went to some quantum mechanics of de Broglie wavelength is lambda equal to h upon b. H is the Planck constant, p is the momentum. We saw the Heisenberg uncertainty principles in terms of delta x and delta p. Then we talked about something called the quantum wells, which is essentially your potential as a position of x. So if your potential is infinite, let's say, then this is infinity, and this is a quantum well. So any particle here will be trapped, and we call such thing as quant. And what this caused was quantization of energy. In classical world, that we typically see is that energy is a continuum, can have energies very closely spaced, but that's not the case in this world. It's an asymmetric well. If it's symmetric well, it will be from, let's say, minus L by 2 to L by 2. Then we saw a very peculiar principle of in quantum world, that is, so let's say you have this potential as a position of x, and you have this barrier v naught. So particle is coming, but its energy is e naught. Classically, this particle can never cross the barrier because it has to have energy higher than v naught. It's not the case, but quantum mechanically there can be finite probability of finding the particle here. That is the thing. Quantum world is a relativistic world, and your classical is a deterministic world. And then we all the information, because when you bring the two atoms close together to form a lattice, that is, then what's going to happen is that quantum mechanical effects will come to the picture. And we saw when we close the two atoms and we bring many atoms close together, then we get a periodic potential. We applied something, we used something called the Ronick-Penny model, and what we got was that the orbitals overlap, and we got something called a band gap. So band gap will look essentially something like this. This is your EC, this is your EV. Electronic states can be below EV, above EC, but this is the forbidden gap. This we call the EG, right? And we also saw these are actually not flat. So if you draw the EK curve, this is called the dispersion relation, you see something like this. So this is your valence band, this is valence band, this is your conduction band. The curve can be used to determine the effective mass, and effective mass is a very powerful tool, in the sense that we can just forget about quantum mechanics in this world, and what we can do is simply use our understanding of the use your classical expressions like F equal to ma. Instead of using this, we'll just star m star, where m star is your effective mass. So that's the power of effective mass. Then we see we can dope the semiconductor. So usually intrinsic semiconductor Fermi level lies exactly at the middle. This is not the case for doped semiconductor. For n type, this will move up. For p type, this will move towards the EV. This is something called determined by the Fermi function, with the probability of finding the electron is half. We have seen that in our slides. This is a function that we saw, and we use quantum mechanics like density of states and whatnot to find the carrier concentration, and we saw that we condensed them to something called NC and B, and Ni was the important thing which we used to call the intrinsic carrier concentration. And then we saw how this carrier concentration change as a function of temperature. You can also have non-uniform doping. In that sense, you can have your bands will not be flat, EC and EV. They can be something like this, right? And when there is a slope in the potential, you'll always have a field which you call the built-in electric field. Now what you do is that, for whatever reason, if there is a electric field applied to a charge carrier, let's say electron, what it's going to happen, it's going to move, like F equal to Q times electric field. That's what we know. This can be written as m star A, right? So it will move, and we saw this is something given by mobility. So we saw Vd equal to mu times E, sorry, where mu is the mobility, E is the applied electric field, right? And it can also diffuse a charge carrier. For instance, if the higher concentration of electrons on one side, they'll move to a concentration of lower side, right? Total current is given by the drift current plus diffusion current. That is the current due to the drifting of the charge carriers as well as their diffusion, and the Einstein relation links the mobility and the diffusion constant D. And the semiconductor, for instance, what we talked about is at equilibrium. It need not be at equilibrium. So for instance, we can apply some electric field, inject some carriers through a battery, or we can shine light. We saw that in optoelectronic devices. They can recombine also. All this effect we saw in the minority carrier diffusion equation. right? And then we condense all this information to form a p-n junction, that is p-type semiconductor on other, and on the right, the holes will diffuse from left to right, right? So but the leave behind is a negative charge carrier, negative lattice stored charge here, and positive on the other side. Now there will be an electric field. We saw that there will be electric field here. This is the depletion region known as the depletion width. This is the stored charge, and there's a built-in potential. And we use something called the depletion approximation, and these are the quasi-neutral regions where you don't have a depletion region, right? We don't have depletion. Okay, and then we saw this band diagram of a p-n junction. It used to look something like this, right? This is your p side, this is your depletion region, this is something called, we call the built-in potential, VBI. So you have a Fermi level at equilibrium, something like this. However, if you apply a positive bias, that a forward bias, that is p to the positive terminal of the battery and to the negative, you lower this barrier and the charge carriers can diffuse and there will be a large current. In the reverse bias, however, this depletion region will widen and you'll have very small current. That will only be due to the drift of carriers which come to the near the depletion region. And in the reverse side, which you can see, there's a charge that is separating, which I draw in the earlier. So remember, negative one here, positive here. So that as a charge separation in space, there's something capacitance associated, which we call the junction capacitance. Then we saw the second type of junction called the Schottky metal semiconductor junction. Again, we saw that how, depending on the work function of metal or semiconductor, it can be a Schottky contact. And Schottky contacts are of two types basically: rectifying contact or ohmic contact, right? And the basic difference from the p-n junction was that the emission here is thermionic. So as soon as the Schottky barrier is crossed, right, the electrons can travel, and the saturation current is also higher here. These are useful because they are faster, okay, than p-n junctions. MOSCAP is the thing which I'm going to primarily discuss today, so let's just skip that for now. And also their capacitance voltage characteristics, and using MOSCAP we created something called a MOSFET. We'll touch upon this, and we saw the different regimes in which it operates. So if you remember your ID versus VD, the curve used to look something like this. So this is our linear regime, this is our saturation regime after the channel pinch off, and this is the square law where we use the gradual channel approximation. And we saw that this is a 4-terminal device essentially, right? So the body is also there, and bias can affect the threshold voltage. And we saw the MOSFET scaling, that Moore's law, every generation the transistors will double, proposed by Dennard. And then we effectively saw the short channel MOSFET. In that we saw that velocity, the saturation will hit early. Velocity, it happens to the velocity saturation because the drift velocity saturates due to the reaching of the critical electric field. Remember we talked about VD equal to mu E. So VD looks something like this. So what's happening is a short channel MOSFET operates somewhere over here. Long channel is here. Okay, so due to the velocity cannot increase any further, the current saturates. And one more effect we saw, the channel length modulation, is the pinch off keeps getting shifted, pinch off point keeps getting shifted to the left, and which we saw there, the ID, the current expression, you change something like this, that ID is sat 1 plus lambda VDS. This is true only in saturation. Channel length modulation will not play any role for, let's say, in linear region. We saw why we use high-K dielectric or the FinFETs, those new technologies. Then we switched to optoelectronic devices, where essentially we are talking about photons. We talked about the role of direct and indirect band gaps. The first device you saw, solar cell, which operates in photovoltaic mode. We saw what we mean by dark current. So let me just clarify this. So this is our PN diode in the dotted line, and we saw that if some devices can operate over here. So solar cell operates in this quadrant, the photovoltaic mode. On the other hand, photodiode or detector works here. This is the dark current that you see. Sorry, this is wrong. So it is something like this. This is incorrect. Just hold on a second. Let me erase it to avoid any confusions. Yeah. Okay. So yeah, this is your I versus V. And we saw dark current, the critical things like open circuit voltage, which is this, short circuit current, which is this, and we saw discuss something called the fill factor, in a solar cell, and the maximum power and the efficiency. Similarly, we saw responsivity for a photodiode. Finally, in the last session, we saw this some radiative process in semiconductor, like absorption. If you shine a photon of sufficient energy, it can get absorbed, and once the electron gets excited, it can just fall back to the valence band, leading to spontaneous emission. However, we can have stimulated emission, which leads to lasers. However, that also needs population inversion, and you must have some gain, the cavity to excite, to have only one to have only specific frequencies to survive. That's why a laser gives a monochromatic light. FWHM is very low, and we saw the double heterostructure in this case. LEDs for spontaneous emission, we use LEDs. Spontaneous emission, sorry, use LEDs, light emitting diodes. There we need a direct band gap for efficient LEDs, to make efficient LEDs. The substrate is very important. So for instance, lattice mismatch has to be minimal to avoid the defects. We saw something called radiative and non-radiative lifetime, which in turn was linked to the internal and external quantum efficiency. So internal quantum efficiency is essentially your photons generated. Can someone tell me what was internal quantum efficiency?
Number of photons generated upon number of photons incident for internal quantum efficiency, and for external quantum efficiency, it is the number of photons that has been emitted divided by number of photons which has been generated.
So why are we making photons incident on in internal quantum efficiency? You said we incident some photons. Why are we incidenting the photons? LED is something which converts light to electricity.
Sir, it
Electricity.
is electroluminescence device. So it is number of photons which has been injected, that is pumped.
Yes, correct. No, okay, I must have heard it wrong. This is the injection, right? So how many charge carriers we are injecting? Essentially, this tells you if I'm let's say injecting 100 units of charge, uh, how many of them will be able to generate photons. So that's internal to the device. However, there are some other considerations like refractive index, the cladding, and so on. So what, as consumers, we worried only about the external quantum efficiency, which you talked about as the extracted upon generated. Both of these terms are important. For a device, for a research perspective, internal quantum efficiency is one of the people focus more on that, because the materials research and whatnot happens in this area. So materials research also happens, so this is very important, but here this is more of an more oriented toward industry. That's what I would say. All right. So as I told, we'll have around, yeah, we have around 50 minutes, and today I'll revise the MOS capacitor. So why I chose this topic, because it was covering at least at least 3 weeks, and plus the MOSFET devices that we read about. And MOSFET is the bulk of is a semiconductor device which is present in your phones and everything. Um, Virtually everything, I should not say everything, many of the products that you see in our daily life today are based on MOSFETs. To understand how a MOSFET works, we need to have an understanding how a MOS capacitor works. All right. So what we have, as the name suggests, metal oxide in semiconductor. This oxide is usually an insulator, right? So for instance, if we talk about silicon here, right, so this is typically silicon dioxide. That's why the term oxide came. And finally, we have a metal on top. So this terminal is also referred to as a gate. There is no gate here per se, because gate is used to control the flow between source and drain. Here there is no source and drain, but I'll be using this terminology. And this terminal that you see is called the body terminal or substrate. There are different terms that are used for this, so I'll be using these terms interchangeably. Okay. Right, and there are some assumptions that are, because if you try to understand the working of a MOSFET, I told you we first need to understand MOSCAP, and even the MOSCAP that we are considering here is an ideal MOSCAP. Okay, so what we mean by that is that metal semiconductor Fermi levels are the same. So that means the verb function is the same. So if you recall, in Schottky barrier we used to draw this vacuum level, right? Vacuum level, and there this was the Fermi level on the metal side, so it will be filled all here, right? And there will be some oxide here. Let's forget about oxide. Let me draw the semiconductor. I'm drawing the Fermi level of the semiconductor here, EF, and I'm assuming the semiconductor to be p type. in this problem. So what will happen, EF should be closer to EV, so it will be some, this will be EV, and this will be somewhere here EC. So you see EF is closer to, it's not very clear, let me redraw it. So let me draw EC over here. Okay, so it's a p-type semiconductor. You can see EF are at the same level. This is what we mean the Fermi levels are the same. They need not be the same, which will break this assumption later, but for now let's keep this. And no traps at the semiconductor oxide interface. So remember there's an oxide here. So whenever different materials are there are defects always. So here we are assuming it's a perfect interface. To be honest, silicon and silicon dioxide is a very good interface. The nature has made it so. So we can still engineer it, yes, but nature itself has given it that silicon dioxide form a very good interface. The traps by themselves are low and the defects are low. And metal should be thick enough for an equipotential surface, because if the this is essentially this stems from electrostatics. If it's not if there is thickness variation, we want the potential everywhere to be the same, right? Finally, the semiconductor thickness is larger than the maximum depletion region thickness. So we'll see that this gray region you see, this is the depletion region. So we don't want entire semiconductor to be depleted. This is more or less satisfied. This we don't want it. This is also more or less satisfied. And oxide is a perfect insulator. This also is violated to a certain sense. So please remember, these materials that we are growing, they are defects. So there are many kinds of defects. So under stress they can crack, or some, if you apply some electrical potential, they might crack. Perfect insulator means there will be no transport of electrons, no transfer of electrons or holes for that matter. What this means is that you, at this terminal, even if you're applying some bias, you cannot push or pull out any electrons or holes. So this is a perfect insulator. And this is the oxide that I was talking about, silicon dioxide. Okay, so this is this question is stems from the by the way we name a device. Okay, so when we are discussing something, we must understand what we are talking about. So this is the problem here that we have. So just a second, sorry. Yeah, so the questions are, choose the correct statements from the following. So it says PMOS devices have holes as inversion charge. So there are two kinds of devices, NMOS and PMOS. Okay, so NMOS is basically your metal oxide semiconductor. So basically this terminology we use for MOSCAP as well as MOSFET. So please just keep that in mind. But here we are considering only the MOSCAP. Sorry. So just tell me which one is the correct. Which ones are the correct options here? So PMOS devices, how do they look like, and what's the inversion charge there? We'll talk about inversion charge in a minute, but let's just talk about the nomenclature here. So let's first try to identify this. So we have, this is the EF, this is the EV, this is the EC, and you can see that yeah, so we have applied some voltage, that's why these bends are bent. How are they bent? Let's just forget about that. You see here, so this is a p-type substrate, right? And you look at this interface, the oxide and the semiconductor interface over here, you see EF is closer to EC rather than compared to EV. In bulk, EF is closer to EV, but on the interface, EF is closer to EC. This means here it's behaving like an N-type, or I should say electron concentration more than hole concentration, in fact much larger, because it goes exponentially, right, here at the interface, right? So what we this is what we call as the inversion layer of electrons. Why the name inversion? The substrate is supposed to behave a p-type, so it should have excess of holes, but here it has excess of electrons. This means the nature of the material has been inverted, right? And that's why we call it an inversion layer of electrons. All right, so inversion layer of electrons. So so this device, which is of a p-type substrate, will have an inversion layer of electrons, right? And such type of a device which is an inversion layer of electrons is known as an NMOS. Okay, So we have in NMOS devices have electrons as inversion charge. This is one of the correct options. Similarly, the other case, again we have EC here, EF here, and EV. The black line that you see is EI, the intrinsic level, which lies near the midpoint of EC and EV. So you see when EC and EV are bending, EI is also bending. EF stays flat because we are talking about the equilibrium condition here. Okay, so now what's going to happen? So let's say in the bulk it's n-type. You can see why, because EF is closer to EC. We talked about when we talk about the Fermi levels here. I just referred to again in the short summary here that if EF is closer to EC, this means it's n-type. Okay, but you look again at the interface. So EF is here and it's closer to EV as compared to EC. So again, on the interface, what we have is hole concentration. So holes larger than electrons. What this means is that we have an inversion, and this is an inversion layer of holes. Again, why the term inversion? Because this substrate was supposed to have an excess of electrons because we doped it n-type. However, this interface, due to the electric fields and whatnot, we'll see in a minute. So what's happening here is that we have an inversion layer of holes, correct? And this type of device is known as a PMOS. This was NMOS. So PMOS devices have holes as inversion charge. This one. So the thing to remember is that a device is named after the nature of inversion charge. So this is the key thing that to remember. So here the inversion charge is electrons n-type, hence is an NMOS, but the substrate must be p-type. Okay, so now we try to understand that how does this inversion layer even form. So first we have a flat band condition. So you can see, so what we have is the flat band means the bands are flat. So remember that the assumptions that we had of an ideal MOSCAP, oxides have no traps and the Fermi levels are the work functions are aligned and whatnot. This is a flat band condition, so nothing is happening. So electrons wherever they are. So here this is a p-type substrate, as you can see EF is closer to EV. Right, so what I'm going to do now is now I'm going to apply a negative potential on the gate. Okay, if I apply negative potential on the gate, just see what's going to happen. There's concentration of holes here because this substrate is p-type, this material is p-type. So it's going to happen, yeah, some of the potential will drop here, but some electric field lines will reach here. What they'll do is attract the holes because the applied potential is negative. They'll attract the holes and the holes will accumulate here. So again, you see at this interface, EF is closer to EV as here as compared to in this region, right? So what we see is that in accumulation, holes get attracted towards the oxide semiconductor interface. Sometimes this interface is also referred to as surface. So just please don't get confused. Surface is not this. The surface, when we say surface, we mean this. Okay, so now let's do the opposite case, right? Let's now apply a positive potential to this. This is our reference. Let's say this is a reference from where we are applying the potential. So when we apply positive potential, what's going to happen is you can clearly see if you apply positive potential, you'll repel the holes away, right? So how will you denote that here? So you can see here that the EF will now start to move. This is EV, this is EC. So just look at this region. Now EF is almost at the midpoint. It's coinciding almost with EI at the surface. The oxide semiconductor interface, it's almost coinciding with that. So this means what we have done is that, and the other so we have started doing that, but what we are doing in return is that now since we are repelling the holes, what's going to happen is going to expose the acceptors, right? Since the p-type, so you repel the holes. These are the negative the dopants that you have. This is the depletion region, because this region is devoid of mobile charge carriers. There is charge, but no mobile charge carriers. This is the definition of depletion. And the whole concentration has reduced as compared to this bulk here, right? In the depletion region, whole concentration has reduced. What happens if you increase the bias even further? If you increase the bias even further, what you see is that now EF will now even cross this EI. This is your EI, right? And there are some specific conditions when do we say, but this is inversion now. Why inversion? Because as soon as it crosses EF, as soon as it crosses EI at this quote unquote surface, what's going to happen, the nature of material at this interface changes. Now it's behaving like an n-type, right? So nature of material changes at the oxide semiconductor interface. So nature has changed, and how do we denote that? We denote that by saying that now EF has crossed the EI at the surface, so to speak. This is what we call as inversion. So this is a very key term. Depletion, we read about or hear about this in terms of PN junction, Schottky junction, but this is the first time that we are introduced to the term of inversion only in the MOS capacitors. And also, since MOSFET is a device that uses the crux of MOS capacitor, this term we also see in case of MOSFET, field effect transistor. Okay, so that's how it operates. So essentially you have what we refer to as the four regimes. So you have a flat band, you have accumulation, depletion, and inversion. So it can be in either four of these regions depending on the gate bias, by VG, or the bias at the metal that you are applying. And just to be very clear, what I mean, the circuit has to be complete. So this is our metal, this is metal, and then below that we have our oxide, and then here we have the semiconductor, say P type. Okay, and the other terminal is here. So what you're doing here is essentially you're doing something like this. This is the VG that I'm talking about. So that's how you bias this circuit. So VG, if it's 0, so essentially the body is grounded, as well as the metal. This is the metal. Now you turn the knob of VG to negative, then you have accumulation. If you turn positive, you have depletion, and if you increase the voltage even further, the gate voltage or the metal voltage, you'll enter the inversion regime. Okay, so these are some things to identify just from a given band diagram. We need to identify the type of the substrate and MOSFET in this problem. So how do we identify the substrate? So first you just see in the bulk we see the nature of the material. So we have EF as this is our EV. So we know first one is nothing but your this is EF is closer to EV. So this is a P-type semiconductor, right? So we write this is a P-type, and we have also noted that P-type semiconductor gives rise to NMOS if it's inverted, right? Here it's an accumulation case. We'll see but this is P-type, so P-type can give rise to a NMOS. So we have P-type, and so this is incorrect, this is incorrect, and this is also incorrect. P-type NMOS. Okay, so it's going to be either third or fifth option. Let's look at the second device. So second device, this is our EF, this is our EC. EF is closer to EC, so this is an N-type device. An N-type device gives rise to a PMOS. So this is incorrect, this is incorrect, this may be correct, this may be correct, this is incorrect. So again we have these three, so we have to look for the third device now. So this is our EF, this is our EV, again in the bulk. So we are checking here only in the bulk. So again EF is closer to EV, so this is a P-type device, and P-type device gives rise to NMOS. So P-type NMOS is incorrect, this is incorrect, so this option. is the correct, right? Because if we want to analyze it further just by looking at the band diagram, we must first identify the type of device. Okay, so that's how you do that, just by looking at the bulk, how it's behaving. You can say it's NMOS or PMOS, because so later when you try to solve numericals, for instance, right, you need to know the threshold voltage. Yeah, it's because there's a modulus there, negative or positive, and there are some other considerations when you design the circuit. So this is a good practice to identify the device just by looking at the band diagram itself, right? And secondly, an even better practice, or I should say the next step, is to, just by looking at the band diagram, which regime you are operating in. So remember, we talked about the four things: flat band, accumulation, depletion, and inversion. So those are the four regimes. So in this problem again, we have to identify that regime. Okay, so we saw that. So first, this was p type. So p type means it was an NMOS. Device 1 was NMOS, right? So NMOS, and you can see that the EF is even closer to your so there is an excess of holes here, right? And you see the holes concentration is increased on the oxide semiconductor interface. This means we are talking about accumulation here, accumulation of holes rather, because the nature is still p type and the holes concentration is increased as compared to the bulk. So when will holes accumulate here? When you apply a negative potential. If you apply a negative potential to the gate, the holes will get attracted to this interface. They cannot pass through the oxide. Remember, it's a perfect oxide. It's a perfect insulator, sorry. So no electrons or holes can pass through the oxide. Okay, and neither they can get trapped. So we have those two assumptions are still valid here. So we have accumulation of holes here, and when they will accumulate when Vg is negative, right? So when Vg is negative, so this is incorrect. Vg is negative, and we have accumulation here. This is incorrect. This is incorrect. This is also incorrect. So we have negative and accumulation. Let's we know our answer, but let's solve for second device also. So first, this is EF and this EC. So this is an N-type device. N-type semiconductor. So we'll formulate a PMOS here. So let's see what's happening at this interface. Let's see. So EF is even closer to EC here. So here, whatever the concentration of electrons, EF is closer to EC, but EF is close to EC, but it's even closer here. So what's happening again? Again an accumulation, because you're not changing the nature. Remember that it's N-type here, it's N-type here. Only the concentration has increased because the EC and EF levels are even closer. Remember that expression, N equal to NC. This expression, N equal to NC exponential of EC minus EF over KT. So this is the driving force. When I say concentration is increases exponentially. So here we have accumulation of electrons, right? And when will the electrons accumulate here? If you apply positive charge. If you apply a positive charge, the electrons from this semiconductor will accumulate at the oxide semiconductor interface. So we know Vg has to be positive, right? For second device, so Vg has to be positive and accumulation. So this can be correct. This can be correct. Yeah, positive and accumulation. Third device, again EF and EV. This is a p-type device, so we can formulate NMOS here. And now we see an inversion. Why? Because this here it's behaving p-type, or let me say excess holes. Here EF is closer to EC, so what we have? Excess electrons. From excess holes to excess electrons, this means we have inverted the nature of this device, of this semiconductor. So we have an inversion. And secondly, if we saw that this is a p-type device, right? So when will that invert it? To go to inversion, we must have depletion first. To have inversion, semiconductor must be depleted first, right? So in order to deplete a p-type semiconductor, you have to apply a positive bias, because then it will repel the holes away which are present in the semiconductor, right? This means the Vg has to be positive. So Vg, this means positive Vg, because we are talking about an NMOS here. Okay, so positive Vg. So we must have positive Vg, and we'll have inversion. So this is not correct, not correct. Not correct, not correct. So what we have here is option C, this option. As I was saying, this is a very handy thing to analyze the basic characteristics of a device just by looking at the band diagrams. And to do that, you must also learn that, so what do the curves in each of them mean. So so you can see the curve here in accumulation as well as in depletion, right? Which is which. So for that you also need EF, the knowledge about EF and its distance, so to speak, with the valence band or the conduction band, depending on the type of semiconductor the doping we are talking about. Okay. The third set here we have is wait, yeah, again a similar exercise essentially. So let's do this quickly. So this is EF and this is EV. So what we know, this is a p-type semiconductor and it will have NMOS. All right, so we have p-type and NMOS, right? And then EF is closer to EC. So this is N-type and it will form PMOS, right? So this option will be the correct. Third one, you can see again, this is an N-type, it will form a PMOS. So this and this. Okay, I think I mistakenly took these questions again. Okay, let's forget about them. Let's move to next set of problems. This gives a, now the this problem we saw in only in terms of band diagram, right? The second level that which you must which it's very useful to understanding is to the charge profile, that how do the charge profile look like. Because essentially, see, there is a, whenever you are applying external electric field, when you are applying biasing, essentially you're applying electric field, so that will cause the charges in the semiconductor to move around. Again, oxide cannot play a role because you're assuming it to be a perfect insulator, right? So the charges have to move around here, they have to be balanced, right? Because essentially no current can flow, this oxide will block any current. So EF has to be flat at the end of the day, right? Because no current is flowing through MOSCAP, please remember that. No current flows through MOSCAP. That's why we are drawing flat EF. It's an equilibrium. Okay. So now let's try to do the charge profiles for this. Now we have understood which regimes they operate in, right? So let's do the for the first one again. EF is now closer to EV. So what we mean is that this is a p-type substrate. First step, always identify the substrate. This is a p-type, right? And we can see that the distance between EF and EV has grown, right? In fact, it's almost intrinsic at this interface. Okay. Now when will that happen? So that will happen when you repel the holes away, because there's this substantial amount of holes due to this doping. When will you repel the hole away? When you apply a positive VG. If you apply a positive VG, so the holes which are there will get repelled and you will leave behind the stored charge, the negative charge. Okay. Applying positive VG, so that's why you see this blue curve, that blue block you are seeing is you're applying on the metal. That is true for both of them, or in fact for all the three diagrams. The key difference being there is a negative stored charge that we see here, right? And we do not see any inversion because it is not, because at this interface it is intrinsic, perfectly intrinsic, so to speak, right? So we do not have any inversion layer. So this green block that you see is for inversion. What we're seeing is that on the metal we have a positive charge, and inside the semiconductor, so oxide, you see no charges. This is the oxide, right? You see no charges here, and we see a negative charge, the depletion, the stored charge which will be here. Okay, so this will be the correct diagram. So it is in depletion, we have established that, and so first will match with C and it is depleted. So this is not correct, this is not correct, this is not correct, this is, sorry about that, last option is also not correct. First will match with C and depletion. Let's look at second. Second is, again you see EF is closer to EV in the bulk, so again it's a p-type. Now let's look at what's happening at the oxide semiconductor interface. So we see that oxide semiconductor interface, EF is closer to EC, but in the bulk EF is closer to EV. So this means we have an inversion layer of electrons here, correct? Inversion has happened. So inversion we are denoting by this charge, by minus Q. When will that happen? Only when we have depletion first. So depletion we saw will happen at positive bias. So Vg here will also be positive. In fact, even higher than what we have in depletion case, in the case 1. So Vg will be positive, and we'll have depletion, which we denote by this red block. Also we have this green block of inversion charge, which is over here, right? So we'll have 2 matching with A and in inversion. So this is correct. 3. So this, you see, this is n type, because EC is closer, EF is closer to EC, sorry. And you see at this interface, EF and EC distance has even, they have come even closer. This means concentration of electrons has increased at the interface more than in the bulk. The nature has not changed. This is what is referred to as accumulation. So 3 has accumulation. When will the electrons accumulate? When you have positive, when Vg is positive, they'll attract the electrons at this interface, right? So this, and you have only accumulation of negative charge. 3B. Okay, and this is a good exercise in the sense that I am applying positive bias in all the 3 cases on the metal, but they are behaving differently depending on the nature of the material as well as the extent of the metal charge that I am applying, all the voltage. Okay, now let's go to the second part of a MOSCAP, which is where we see the characteristics. So here what we are doing, we are changing the voltage. We'll see how we are changing the voltage, but let's just understand the system. So you have metal oxide and semiconductor over here, and what you are doing is that so right now what we are seeing is the flat band condition. Okay, so there is no bias that is applied, so everything is fine, or you can even say they're ground and they're short. Okay, so we're not seeing anything, everything is fine. Now we know that when we apply, let's say, positive bias Vg, so I'm assuming this semiconductor to be p type. Okay, so let's apply I apply some DC bias. So applied voltage will be equal to Vg. This will change now, right? Depending on the value of Vg, it will behave differently. We have seen that when EF is closer to EC, so if we apply a negative bias, we'll have accumulation. This is how the profile will look like. So negative bias we're applying, that's why it's minus Q here, and the holes will get accumulated because negative bias will attract the holes. You can see EF has been, sorry, this is EV, my bad. EF has now moved closer to EV. What will happen now? What we do is now if we apply a small sinusoidal voltage, okay, Vs sin omega t, apart from this DC voltage, but the total voltage will be DC plus AC, right? And then we try to see how this is going to behave. Okay, how is going to behave? So we will add some extra charge over here. How do we do that? So please remember that dq equal to cdv. Wait 1 second. Yeah, correct. dq is cdv. So I'm changing capacitance. I'm assuming to be constant, right? And I'm only applying a small change in voltage. So I'll see a small extra change in dq. Or alternatively, you can see I'm trying to deposit some extra charge delta q here on the negative side itself. How will the device respond? So device, the charge neutrality has to be maintained. So an extra charge will be added here because the whatever the holes are there, if I'm applying a slightly negative bias, this black square that you're seeing, I'm applying this extra negative charge. So device will quickly respond to me and say that okay, we are giving this extra positive charge because there's plenty of holes, right? This is for p type. That's how it will behave, right? So what is the C accumulation? What is the capacitance? So we can see the capacitance here is delta Q over delta V, which is that nothing but Cox. What is the oxide that's seeing here? So you're depositing some charge over here, and you're depositing some charge over here, correct? That's the extra charge with the change in voltage. This will be Cox. Pardon me, this is Cox. Cox is the oxide capacitance. So oxide, this will be equal to, let's say, epsilon naught epsilon ox area epsilon A by thickness of oxide, Tox. This is the Tox. And let's plot this in this CV plot. So what we do is that we usually normalize with respect to C oxide. So let's obtain C by C ox, right? So this will come out to be 1. C accumulation is nothing but C ox. And this is the accumulation region. Remember what voltage we are applying? We are applying a negative bias. So for this whole region, we'll have something like this. This is, let's say, we are calling the value 1. Okay, now what we do, this was the flat band condition, and now I apply a positive bias, only DC. So and now I am just I'm not, it's the bias is low enough, so we are only in depletion. So please see that here EF is closer to EV, so this is a p-type semiconductor again that we have, right? And at this and we are applying some positive bias, so what's going to happen, it will repel away the holes, right? And when it repels away, so whatever the dopant charges will be negative in this case, they'll be exposed in the depletion region. And again, the depletion approximation that I referred to in the for when I was talking about the diodes, PN junction diodes, this is same valid. So this is a depletion approximation, we're still following that. Okay, so we have this minus Q over here, this depletion charge will form. Note that we have not inverted it yet. This means Vg is positive but not very high. We just have a depletion layer that is forming here. Okay, so now we'll do the same exercise as the last time. That is, we'll apply a small AC bias to this. Okay, so this will be the total applied signal. How will it change? So what I'm doing essentially, I'm depositing some extra, no, please note that charge is positive in this case, metal charge that is, because Vg we are applying is the positive bias. All right. So what I'm doing here is that this is the delta Q that I'm adding. So again, this dq or delta Q will be nothing but CdV. Right. And from here we'll try to extract the capacitance. So I've added some dq. So what's going to happen now, as you add some charge, let's say delta Q over here, essentially you're applying a higher positive bias, right? What's going to happen is the depletion width is going to increase by some bit dw, right? And dw will have a corresponding charge over here, because remember the total charge that I'm talking about will be Na, the accepted doping. This is in Cm minus 3 times A times depletion width. This is the depletion charge, Q depletion. Na accepted doping times the area of the device times depletion width W. So if you change the potential over here, which we are doing here, applying this very small, if we change the potential here, so depletion width will change. Note that depletion width also depends on the applied bias, right? Same thing here. So the depletion width will change, the depletion charge will change. All right. Okay, but what we are seeing here is that this capacitance is not straightforward. This capacitance you will still see. This one. So let's say where is the charge getting charge is here, the charge is getting added here. So we have these two capacitances in series, Cox and what I'm calling of this region as C depletion. Cox and C depletion are in series. Cox and C depletion are in series. You can see them. For let's say the corresponding charge, it's here. So this is, you have to cross Cox as well as this red region, this red depletion region, this region that we have. Okay, and when capacitances are in series, the effective capacitance is nothing but you put them in parallel. So essentially what we are doing, 1 over C equal to 1 over Cox plus 1 over C dep. And Cox we already know, it's epsilon ox A by T ox. C dep we can also find out. And so how it's going to behave, so let's say now we have changed this we have already done, this is in the accumulation. Now we are in depletion, so as we see we have to draw somewhere in this region. Okay, so what's going to happen, so as W will keep on increasing, right? So let's say you keep on piling up the charges here, right? So what's going to happen to depletion region? So depletion capacitance, so you can speak, it will depend inversely on your depletion width, correct? Just like it was epsilon ox by T ox, this has to be like epsilon semiconductor divided by the depletion width over here. Depletion width goes on increasing, so this value will keep on getting smaller and smaller, right? This value will keep on getting smaller and smaller, and thus this will dominate. So see the larger terms, because if you have to identify in this kind of expression which term will dominate, the smaller term dominates if there's significant difference between them. And C depletion will keep on reducing as you increase the voltage. So dV increases, this means W increases, this means let's say dW increases, and then CW will decrease. CW will decrease, this means this capacitance C will also keep on decreasing. So this follows something like this, of a trend. The start obviously here from Cox, but after certain time C depletion may start to dominate. Okay, this is just half the picture. This is not half the picture, I mean, on the positive side this is half the picture. The next state that we know is that after flat band you apply some negative positive bias in for a p-type semiconductor, you will enter depletion. And finally what we have, if you further increase the bias, you'll enter something called the inversion. So you see the inversion chart that is formed here, and this is the band diagram. You can see EF is now closer to EC as compared to EV. This means the nature at the interface is different as from the bulk. This is what we refer to as inversion, correct? And this is how the charge profile looks like. We have seen this. Now again we'll do the same. We'll add a small signal, this AC small signal, to the DC bias that we already have, and how it's going to behave. So first thing is that what's referred to as LFCV, low frequency CV. This means this omega is changing very slow, or let's say slow. Now slow compared to what? That's the question. That's what we'll see here. So what again we are doing, if we are increasing, let's say Vs, the positive cycle, some more extra charge, this delta Q, will be now put on the plate. To balance it, a negative charge has to come. A negative charge can come either in the green region or in the red region, or in both the regions, right? Here we are changing the frequency slow enough. This means this takes time to accumulate this this delta Q, denoted in black square here. What's happening is that this means that we change it slow enough, the bias here, such that the electrons get time to travel to this interface. Because remember, electrons, where are the electrons coming from? Electrons are coming from your semiconductor here. They have to physically travel this distance, right? So in order to do that, if we give them sufficient time, they'll be able to generate and they'll be able to travel this depletion width, right? And that's why if we are giving sufficient time, this means frequency is low enough and the charge will accumulate over here. Okay, and it will be contributed to the inversions. Obviously the polarity will be inverse. If it's positive, it will be negative, right? So again we see that how C will be equal to dq over dv, right? And so charge that is being added is only being added across Cox. This is the only capacitance that is in between these two charges, right? So what we see is that in low frequency CV, so this is in the depletion region, so this is the accumulation region that we have, this is the depletion region that we had. Third region that we are talking about here is the inversion region. So for low frequency, you see it has to be Cox, and we're writing C over Cox. This should be 1 then. This means it should be here. This is for low frequency CV. This is LFCV, low frequency CV. That's how it will look in the inversion region. So here from I'll draw in dotted. So inside this dotted square, you have the inversion region. Okay, let's do the second case now. That's when frequency is changing fast. This charge is being accumulated here. However, it cannot respond. The electrons do not have sufficient time to get generated and travel this depletion width to come here. What's going to happen? The charge still has to be balanced. This means the holes can move, right? And the depletion width will increase. So here again, this is the same case that we had in depletion. This was Cox, this was your C dep, right? And here, if you recall, C effective was Cox parallel to C depletion, right? And so how it's going to look like? It's going to look like something that we, just a second. Yeah, it's going to look something like this. This is the LFCV that I had drawn. HFCV will not move because see, what I'm saying is that C depletion dominates so much that it's going to be determined by that itself. All right. So yeah, so that's how this is the two regimes, and this is how we can, in fact, this is a very powerful tool to establish that in which region we are operating in, or which frequency we are operating in for that matter. If you see as a voltage, it remains constant, so you can either be in accumulation or in depletion, right? sorry, in depletion, you see predominantly you will see a decrease in the capacitance. This is normalized capacitance, but absolute values will also decrease, right? And you see a minima here, so it cannot go below that because you have to take their values here. Okay, and as I mentioned that we'll violate some of um, the the assumptions that we had made in ideal MOS capacitor. First thing is that phi ms need not be 0. The phi ms is essentially of the metal semiconductor work function difference. So you see this for metal the work function is here, while this is again a p-type semiconductor. You see its Fermi level is here. So even if you just connect them, there will be a flow of electrons. So here you have electrons at higher energy, at lower energy. What's going to happen? Some electrons will flow here, right? You cannot avoid that, but you can see that even though you have zero bias, you have no flat band. Recall earlier in ideal MOSCAP, if you did not apply any gate bias, you had the bands absolutely flat. This is not the case here anymore, right? We want to avoid that because all the analysis, all the expressions, the physics that we had gone through, we assumed it to be flat band and then we applied some bias. So what we do is that we deliberately we just choose an offset voltage VG. This VG we have to apply so much so as to again achieve the flat band. So essentially what nature is dictating us that you must have this difference and I'll create a no flat band condition. We cheat it. We say okay, we'll apply, we say this is the offset and we'll be fine now because we have now this we now refer to as the flat band condition. Only a reference has changed now. The only thing we have to be reference is phi ms. Rather than being Vg equal to 0, this will be now Vg equal to phi ms. And so this is your expression for threshold voltage. So these are the terms that come from this comes from your inversion, strong inversion, and this comes from your depletion charge, right? So the voltage that we saw just a second, so this voltage that you're seeing here, this is also referred to as the threshold voltage afterward the strong inversion has come, right? And so we add simply a phi ms term to this and we're fine because this is just a voltage difference that we are adding. So this is like offset that we are creating. We just simply mathematically add it. The second thing that is very realistic is that oxide charges are non-zero. So we saw that, remember that we said there are no traps and the charges cannot get trapped. So there are charge traps in oxides, which are usually what we have been found is to be positive, which is being denoted here. So again, this will create a sort of no flat band condition, right? Because it will have an inherent electric field. And again we started our analysis from the point that okay, we are in flat band condition. So how do we do that again? Simply again apply this much offset. We deliberately apply this much offset and we achieve this flat band condition. And from all the analysis of our threshold voltages, of our charge, depletion width, everything, we just offset the Vg by this amount. This phi ms is here, there, both the cases. You can see the phi ms is also there, this thing. It also has trap charges. So that's how the total effect will come out to be this, right? And again the expression, this is just the extra thing that this is your ideal Vt, and this is due to the non-idealities. There are other non-idealities also, but these two terms are how should I say, most prominent ones. So that's why we see them, because it's not always that we can find a metal which will match with that semiconductor. There is a limited number of metals that we can use in fabrication, and there are limited number of semiconductors that we can use to make our devices on, right? So silicon will have a certain, depending on the doping, will have a certain Fermi level. Similarly, the metals that we are using to make contacts, right, the gate contact in this case, they are in certain number. They will have some we may have some metal semiconductor work function difference. Similarly, the oxide that we are growing, we cannot wish away these trap charges. We have to we can try to control them, and we can try to achieve the repeatability, that let's say every time we are getting x cm minus 2 charge, let's say every time we are getting 10 to the power 8 cm minus 2 of charge, the trap oxide charge here, right? So qox, we can try to achieve that, we can make this repeatable, but then we still have to account for that in the electric field. But how will it impact the electric field? It's very simple. You just apply an offset, as simple as that. All right. And Yeah, so this also, this term, the first term that you see in the blue square rectangle, sorry, is also known as flat band. Essentially the definition being the voltage that you must apply to achieve the flat band. So this is on the right side that you see is your ideal case. But first, ideal case will, to reach there, it was assumed that you are in flat band conditions. So first we have to achieve flat band. For this you need to apply only this much voltage.